Okay, in this example, we're going to see a book sliding across a table. So we're interested after the push, so after the hand leaves the book and it's sliding along. So we want to think about our y direction first. And so if we want to do a free body diagram, we're going to draw an arrow up for the normal force. Let's see. So an arrow up for the normal force. So I'm going to call this the force of the normal. And that's the table is exerting a force upward on the book. And I'm going to draw a force down for the force of gravity. Right, so if I were to take that book, so if I have a book on a table, and here's my table, right, and so I've got a force, if I think about my boundary is going to be, so this is my interaction diagram here, so I'll call it interaction diagram. Oops. I'm spelling that wrong. And so what's touching right here, I'm going to have the force of the normal here. And at the center of the object, I'm going to have the force of gravity. So this is Fg. This is Fn. And so I can take those and translate them over. And now if I think about the forces in the x direction, well, my book is slowing down, and that's due to friction. So that's going to happen right here. And the book is traveling this way. So my force of friction is actually along this way. So this is my force of friction. My force of friction is against the direction of motion. So my force of friction is going to be this way. And I'm going to have a motion map for this. And so if I want to draw the motion map and say the book is sliding along here. All right, so here are my positions at equal increments of time. And so the book is slowing down. Something like that. So I'm going to have arrows that look like that. Something like that would be my motion map. Let's see if I advance the slide. Okay, so we're gonna and I have to figure out how to erase. Oh, there we go. All right, so we're gonna do the same thing again with this dry ice. Okay, so we'll start the video. Okay, so looking at that dry ice, the dry ice is sitting on just a thin layer of carbon dioxide gas as that dry ice sublimates, right? It's converted from a solid to a gas, and so there's that little pillow or pocket of gas underneath the dry ice, so there isn't any friction. And so notice too that the time we're interested in is after he gives it a little push. Um, and so what's happening is we can see that the dry ice is moving at a constant velocity. So we're gonna draw our motion map first. And um, so it's moving at a constant velocity. So I'm gonna have um, my dots at the same distance apart. to show that my velocity is the same and it doesn't change over time. Something like that. So when we're moving from left to right. And then if I draw my free body diagram, I'm going to think about the y direction. So I've got the force of the normal up. And again, I should have started with my interaction diagram. So my interaction diagram, I'm going to have a piece of ice on a table. Like that. And so if I draw my boundary, so I'm going to have the force of the normal here on that surface. I'm going to have the force of gravity down. So that's Fg. This is the force of the normal from the table. And so I'll draw that here. Notice that my arrows are the same length or approximately, and there's no arrow in the x direction because there's no force acting on the block of ice. It's moving at a constant velocity, and so no force is acting on it. So remember that Newton's first law says that in order to, an object moves at a constant velocity unless a force is acting on it. And so since our object is moving at a constant velocity, there's no friction since it's on a pillow of air, that we have a free body diagram that only has vectors in the y direction, and the net force on our block of ice is 0. So if we go ahead, I'm going to erase this. All right, so we're going to draw a free body diagram here for the block of ice. Now imagine that we pull on the block of ice. Okay, so here we've got I'm going to draw our boundary, right? And so I've got my force of the normal here from the table. I've got my force of gravity at the center. My arrows should be about the same length. And now I have this force here due to the pull. And so we'll just call it sub P. And so now I can translate that to my free body diagram. So I'm going to have the force of the normal, my force of gravity. These are balanced. And since it's dry ice, I know there's no friction, but there is the pull. So I'm going to have the force of the pull this way. And because I have force of the pull, if I think about my free body diagram, I'm going to start off pulling. And so I'll have my positions are going to, my distance between positions are going to increase. So my velocity is going to increase here with this pull. Right, so I'm going to have an acceleration in that direction. These are my velocities. And so can we pull the dry ice at a constant speed? We cannot. Because there's no friction, we only have one force to the right, and so there's nothing to balance it to be able to have a net force of 0 in the x direction. And so this is what our motion map looks like.